Well, in today's class, I'm going to teach similarity transformation. The standard is geometry m dot g dot srt dot AO2. In this standard, given two figures, use the definition of similarity in terms of similarity transformations to decide if they are similar. Explain using similarity transformations the meaning of similarity for triangles as the equality of all corresponding pairs of angles and the proportionality of all corresponding pairs of sides. Purpose of the day. I will learn to prove or disprove that two given figures are similar using transformations and the definitions of similarity, and also understand the difference between congruency and similarity. Vocabulary. The new terms you'll be learning: dilation, scale factor. In fact, these you learned earlier. Similarity, similar figures, and proportionality. So, what is similarity? Two geometrical objects are called similar if they both have the same shape. Earlier, I discussed by giving an example of where is Eiffel Tower. I hope you remember the same example I'm quoting. So, one is in Las Vegas, one is in France. These two are having the same shape, or one has the same shape as the mirror image of the other. More precisely, one can be obtained from the other by uniformly scaling, either by reducing or maybe expanding, possibly with additional translation, rotation, and reflection. So basically, similarity means I can say that if two objects are having the same shape but maybe of different size, then they are similar figures. Now, what is the criteria means? First one is same shape. Second one is the sides are proportional, and the third one is congruent corresponding angles. The corresponding angles must be of the same measure, but when it comes to sides, they need not be, but they have to be proportional. When it comes to similar polygons, instead of triangles, if I take maybe a quadrilateral, a pentagon, hexagon, and so on, of course, when it comes to triangles, yes, the sides should be proportional and the angles should be equal. Then in this case, triangle ABC similar to triangle DEF because they are having the same shape and same size. When it comes to polygons, the same rule, that is, they should have the same shape and the congruent corresponding angles. The angles must be the same, but when it comes to the sides should be in the same proportion. By the way, here I have taken only four, but you are supposed to take five. The same rule continues. The angles must be congruent and the sides should be in the same ratio. So let's take some example from the worksheet. Well, similarity is almost the same thing as congruence, except similarity figures are the same shape but not necessarily the same size. Here, what I mean. Have you ever been into a store and seen a model like a model car or a model airplane or even one of those? Look at the new buildings we are going to build, kind of models you see in public buildings sometimes. That is similar. So the model of an aeroplane and the real aeroplane are the same shape but differ in size. In the same way, model of a car or maybe a motorbike and the real car or real motorbike are the same shape but differ in size. Here is another example. Let's take these two rectangles. Notice that these two rectangles are the same shape, but one is bigger than the other. How much bigger? Well, notice that if you multiply the sides of the first one, let's take the sides. Let me take, say that, oops, I'm sorry. Let me take my pen. It is 2 inches, and I see that it is 4 inches, right? So, how many times? How many times? Simply like times 2, that gives you 4, right? Let me take the length, and this one is 8 inches. I'm sorry, it is 8 inches. So how many times means it is times 2. So that gives you 8. Therefore, you can say that if you multiply the sides of the first rectangle, any side, let it be length or width, by 2, you get the sides of the second rectangle measurements. This leads us to the ratio of similarity. All this is the ratio of the sides of the smaller shape to the sides of the larger shape. These two have a ratio of 2 over 4 or 1 over 2. That means let's take a ratio of the small rectangle. I'm taking small rectangle. You can take any one of those sides over the big, say, a large rectangle. You can take, for that matter, any side, like length or width. I'm taking here 2 inches, which is width, and the corresponding side, therefore 2 over 4. Can you divide the numerator and the denominator by any value? Means obviously it's by 2. So 2 over 2, that gives me 1. 4 over 2, that gives me 2. So that is 1 over 2. Not only that, you can try taking the other sides. Here I am taking 4 and 8. Therefore, small rectangle length is 4 units or 4 inches. Large rectangle width, that is 8 inches. Therefore, 4 over 8. Can you divide by any value? Yeah, you may think it's either 2 or 4. Always I prefer to take the large number, that is the highest common factor. So when you divide 4 over 4, that gives me 1. 8 over 4, that is 2. So 1 over 2. You see that these two are one and same, so that the ratio of smaller rectangle to larger rectangle, it is 1 over 2 in terms of sides and also the perimeter. In fact, you learned the same thing in the previous topic, that is dilation. Okay, so let's take maybe one more example. This is same as the previous one. I'm trying to compare. This is 2 units and this one is 3 units. And the length is here 4 and this one is 6. Let's see. So small rectangle. You can take any one of those sides, either length or width, but don't forget to take the corresponding side to compare. So if I'm taking, let's say, 2 units, then I have to take the corresponding, which is 3, therefore 2 over 3. How about taking the length? It is 4 and this one is 6. So I can divide both these values, the numerator and denominator, by 2. So 4 divided by 2 gives me 2, 6 divided by 2 gives me 3. So you see that these two are of the same ratios. The sides are of the same ratio. We can take more examples of this kind. Let's take two triangles. These two triangles are similar, so you may take a small rectangle. my apologies, it is a small triangle over large triangle. Okay, it is not necessary to take all the time the small one as numerator and the large one as the denominator. In fact, you can take the other way around, like the large triangle in the numerator and small in the denominator. But the condition is you have to take them in the same, the corresponding sides. So, for example, let's say that, let me take this one is 8 and not 8, let me take maybe some 12 here. Then let me take the other side as let's take this as 16. So small triangle is 9. So I'm taking this side, the corresponding side is 12 here. Obviously, these two values can be divisible by 3. So that gives me 3 3s 9, 3 4s 12. If I take the other sides, that is 12 and 16, so 12, that is one of the sides of the small triangle, and 16 is one of the sides of the large triangle. So I can divide both numerator and denominator by 4. So 12 divided by 4 gives me 3, 16 divided by 4, that gives me 4. So you see that the sides are always in the same ratio, Well, in what way we can use the concept here? Uh, like say that these two figures are similar and the ratio of similarity is 2 over 5. So let me take the important concept, the key part from the question. So the ratio is given 2 over 5. And when it comes to the sides, I see that this is 6 and this one is x. Okay, so this one seems to be the small triangle, and this one seems to be the denominator part is the large triangle. Therefore, the small triangle is here, one of the sides is 6 and the other one is the large triangle side is x. Now let's try to identify what's the value of this one. So here the 6 over x equals to 2 over 5. Then I prefer to use the method of cross multiplication. That means with this denominator, I multiply the other numerator. With this denominator, I multiply the other numerator. Therefore, 6 times 5 equals to 2 times x. So 6 5 are 30, 2 times x. Then let me cancel out by taking the inverse operation, which is the division. X equals to 30 over 2, that gives me 15. X equals to 15 units. Therefore, here it is 15 units. If you are not sure whether your answer is correct or not, you may try checking one of the sides of a small triangle over one of the sides of the large triangle. So that is 6, and whatever we got, that is 15. Can you divide these two values? Obviously by 3 you can. So 6 divided by 3, that gives me 2. 15 divided by 3, 3 5s. Therefore 2 over 5, which is matching with the given ratio of 2 over 5. Really quick, another example here. You can take the large rectangle or small rectangle, or small rectangle or large rectangle. It makes no difference. So let me change this one. So when I talk about the ratio, you can take the numerator as maybe like one of the sides of a large rectangle, As I told you before, you can take either a small rectangle or large in the numerator, and the other one is in the denominator. Okay, just for a change, I am taking the large rectangle in the numerator. So here, large rectangle is one of the sides is here given as 15, and the corresponding sides of the small rectangle it is x. This is equal to, then again, don't forget I'm taking the large rectangle side in the numerator. So this is 7, and this one is the small rectangle side. Therefore, 7 over 5. As I told you before, I prefer to compute this way. This is called as cross multiplication. So 15 times 5, that gives me 7 times x. 15 5s are 75, 7 times x. Then divide, we go for inverse operation, then make use of calculator, and 75 divided by 7. Let me grab my calculator. 75 divided by 7. You can check it. That gives you 11 point, 11 point something. Yeah, it is close to 11, which is 10.71.